Hello, it's Scott Manley here. It's time for another batch of questions from my supporters over at Patreon. Yes, where I attempt to answer questions without the aid of, well, the internet to give me easy answers. Just seeing what I have in this brain up here. The hardest part actually these days is finding all the questions because I've gone through several iterations of this thread at this point. But I think these are all new questions. It'll be really embarrassing if they're not, and I get the answers different this time. But yeah, look, we're gonna get right started here. We have David Stanaway saying, question on the remaining fuel for the James Webb Space Telescope. How predictable is the fuel consumption for station-keeping maneuvers to keep it in the halo orbit of L2? What is the ISP of the different engines and which ones would be used for station keeping? Also, the hypergol engines will sometimes be used for orientation momentum. When would they? Okay. Oh wow, this is a whole lot of things. Basically, look, the thing about these halo orbits is they are somewhat chaotic, and the closer you are to the perfect orbit, the less fuel you need to maintain it, right? Because the rate of divergence from your path is basically proportional to how close you are to that path, and so if they can get their positions very accurate and make their burns very accurate, then they will need less propellant and they should be able to stay in that orbit longer. 5 years was the target. They could very likely get 10 years out of this. I don't know the exact performance of all those thrusters on it, but mainly it'll be using small thrusters most of the time. I'm not sure it even uses the big thrusters for orbit changes at this point, because the big thruster was needed for basically capture into the L2, halo orbit. After that, it needs to be able to fire its engines in all sorts of directions to make sure that it can stay in its orbit. So yeah, basically the accuracy is best guess for 5 years, more likely 10 years, maybe even longer. Maybe new technology or new ideas, new techniques for tracking its orbit will help them predict it further out, because now it's sitting in this orbit, they're going to have actual data coming back on the spacecraft trajectory, and they might realize that some of their models are slightly different from what's in reality and be able to refine those to get better performance or better accuracy. But it really comes down to the navigation people, right, and the actual thrusters. Giacomo Ferrari asks how the roll-up Sunshield covers work on JWST, and honestly, they work very well. Look, I mean, we've seen the animations, right? They have all this rigging that basically comes out. They roll out, and they are attached to various tensioning systems. They'll tension those, hold them apart, because if they have them touching together, then it means that you get more. Then if you get basically 4 layers of these shields touching together, then the heat comes straight through. So you have to separate them so that the heat has a chance to go out sideways. Yeah, I mean, that's really it. You just need to. It's out there. It has these arms that are folded out to tension the whole system and hold it there. And when I say tension, it doesn't need a huge amount of tension because there's no gravity. It's not like they're making a space trampoline. Stephen O'Leary, the easiest fuel to synthesize on Mars is carbon monoxide and oxygen. Is this fuel efficient enough to power a Mars to Earth mission? Yes, it is. If the fuel is not powerful enough to power an Earth to Mars mission, would it be possible to design a rocket engine that could convert between this fuel and another, e.g. methane or methane and oxygen? So look, carbon monoxide engines are these nice sort of theoretical thing. The performance isn't great, but it's certainly sufficient if you want to get a spacecraft into Martian orbit. It would probably require sending less. The nice thing about manufacturing carbon monoxide and oxygen on Mars is that you don't need to get a source of hydrogen. So you trade that for having a bigger spacecraft because you're going to need bigger tanks. It's not, I mean, it's slightly less cryogenic than methane, but that doesn't really matter so much because because oxygen is pretty cryogenic. And the other thing, I guess, is that they have issues with like instability and ignition. They have hard starts on these engines, so they haven't really done enough investigation to decide to hang a mission off the side of this. But it's going to be a long time before We see SpaceX landing things, giant things on Mars that might need refueled by methane. So, it could be that some changes happen in the meantime in terms of rocket technology. What I find more interesting, perhaps, is having something. So we've got helicopters flying around; those are great. I'm wondering if there's some balance point where instead of charging a battery, they use the electrical power to separate carbon monoxide and oxygen into fuels and then burn those to power an engine, therefore getting higher energy density than they could from lithium-ion batteries. There's an idea for you. Okay, Elliot Foss, who I think has asked questions before. I have a question about an idea I had. My idea is like aero braking, but instead you just creating drag, you use the rarefied atmosphere to create lift. I would call it aero-maneuvering. Okay, and you know what we also call this? We call this an aero-gravity assist, right? This is not a new idea. Don't worry, because it's a cool idea that people haven't actually translated into anything useful. But yeah, it's got a whole thing here about the drag will slow the spacecraft down, but the spacecraft can have a lift drag. You can theoretically extract energy. The main idea behind this is that if you do a gravity assist around a planet, right, you get a bigger and bigger deflection in your trajectory as you get closer and closer to the planet, right? But there's a point at which you get so close you're hitting the atmosphere, and therefore you can't turn your spacecraft anymore. And that might limit the gravity assist options available to you. But if you have a spacecraft which has wings and you flip it upside down and you enter into the atmosphere, you can pitch your nose down and use the lift from this atmosphere to turn you a little more than you would get from gravity. Now, there's a balance. The closer you get, obviously, the more drag you're going to get, the more heating you're going to get. So, there's only so far you could go, but there were mission designs that said, well, if we could do this, we could send a space probe to the sun by having a gravity assist at Venus. And that made a lot of sense. Obviously, Parker Solar Probe is doing it via multiple gravity assists, and that's very cool. But there's no, this is not a new idea. Another idea for this was changing inclination in orbit around the Earth by using a winged type spacecraft to dip into the atmosphere and come out the other side. And this feels a little like hypersonic boost glide weapons, which could do something similar to that. But yeah, this is not a new idea. Look for aerogravity assists. I remember hearing about it in the 1990s in connection with a spacecraft concept called Wave Riders. Wave Riders are conic, or they're sort of like V-shaped spacecraft where the edges of the wings touch. I think the way it works is they touch the sonic boom, not the sonic boom, but the stagnation, the cone, the shock cone that is generated by the tip. And that's where it gets the majority of its lift. I was a lot younger then, so maybe I've completely misremembered how this worked. But anyway, they were going to use that. They would go down to Venus, hit it upside down, scream around the inside, and then when they got to their exact moment where they needed to escape, they would flip and they would go flying off into their new target orbit. That is a pretty darn extreme maneuver, and I would love to spend more time learning about this to see if I'm not crazy. Rajesh King, what do you think about near future space weapons? What would they be like? I envisage a kind of missile that is, instead of carrying an explosive payload, carries 4 or 9 single-use sub-caliber railguns that can be fired a few thousand kilometers out. And when the missile gets to about 10 kilometers of the enemy ship, it aims and fires the railguns. This removes trajectory disruption associated with ship-mounted railguns and doesn't require missiles. So this is very cool kind of Expanse-style weapon systems, right? This, like he says, to me, this seems quite bulletproof, but what do you think? Well, it's a railgun. Is it railgun proof? Look, if you have, I'm going to say, if you have fantasies about designing weapon systems like this, there is a game called Children of a Dead Earth, which basically tries to do realistic space combat using as much of the laws of physics that the designer could come up with. And yeah, you can build little drone spacecraft with guns on them if you like. You could also build little drone spacecraft with guns on them and nuclear warheads, right? You can build giant spacecraft and have those with all sorts of interesting armor. I remember people coming up with okay, so we're going to have a layer of aerogel, and then we're going to have graphite under that, and then we're going to have diamond. And the thing was just like doing the math for all this stuff. So look, here's the thing. Space war is one of those things that since everybody can see everything and your accuracy is very hard, it's very easy in space to get things accurately on target. Anything that has a person in it cannot maneuver as fast as something that doesn't have to worry about g-forces. So it's a very dangerous situation to be in. Yeah, I don't know like what kind of sensors or stuff would be involved, but sensors would be incredibly important to detect that you've got these things flying out there. I would suspect that you're going to have some sort of point defense system, like with lasers ideally, but lasers put out a lot of heat, and heat will therefore mean that you have these big thermal radiators, and radiators, they're not that great because they get shot off and they get damaged. Instead you can maybe dump your energy out as boiling water or something like that. Have a bunch of ice, you heat it, steam blows out. That's the back. I'm just going to say, like, if you have any of these fantasies, go and look at Children of a Dead Earth and you will lose yourself in the nuclear warhead designer. Although the nuclear warhead designer isn't that accurate since it misses things like, actual thermonuclear weapons. It sort of stops at boosted fission devices. Okay, Jesper Embring. Thank you, Scott, for all the interesting stuff you share. Q1, would it be technically possible to build a space elevator? Like, maybe not on Earth, but which concepts would be most interesting to try to implement? Well, here's another concept. How about instead of having a static space elevator that goes from the ground to geostationary orbit, there's a couple of alternatives you can try. How about the Indian rope trick, where instead of having a cable, you have a vacuum chamber, right? You have basically a vacuum pipe with little coils around it. And what you do, on one side, you shoot a slug of material up, and it will interact with the magnetic field and get slowed down, and it will transfer its momentum to the tower, holding it upright. And then on the other side, as it reaches the top, and then the piece gets moved over into the parallel tube. That side then uses the magnetic fields to accelerate the object downwards until it reaches the bottom, and then underneath the Earth you've got another thing that puts it up. So the idea is you're holding this tower in place by continuously circulating stuff and stealing the momentum from it. You could also just, instead of having slugs of material, you could have, let's say, like a plasma that is being accelerated, or mercury, right? You could have something that's really high that is held up there continuously. That ought to freak people out. So basically, if this fails, it all falls down. Or how about a momentum exchange tether that dips down into the atmosphere, where you have this giant long structure, maybe 500 kilometers long, and it's in low Earth orbit, and it just sort of it pinwheels around, right, like this, right? It's rotating continuously, and it comes down in such a way that it touches the Earth at a specific time and spot, where you hook on your payload, and then it continues upwards into elliptical orbit. And then at the far side of the Earth, they can ditch things off. So there's an alternate idea that requires less strong material than a traditional space elevator, and is also much more cool in all sorts of ways. The idea is, because the way this is rotating is that it dips down roughly at a rotation speed, so it can actually move a lot slower. Because it's rotating, it's moving a lot slower than orbital velocity, so it doesn't have to worry about re-entry effects in the same way. And most of the mass is still outside of the atmosphere, so it doesn't experience drag in the same way. I like that idea, just because it's so wacky and cool. Blaze Carey. Hi Scott, I love your content. Long vertical side-by-side rocket tanks for propellants. Oh, sorry, Q1. Why don't rockets use long vertical side-by-side tanks for propellants? They're always stacked on top of each other, and I assume there's a reason. The main reason is that it's much simpler, right? So, if you had two narrow pencil, thick tanks side by side, right? Then guess what? You've got more surface area than a single fat tank, so you need more materials. That's why you don't stack them side by side. Now, if you then had a big fat tank and you maybe split it down the middle by a bulkhead in there, again, you have the same problem because the bulkhead is bigger. By having them stacked on top of each other, you're minimizing the bulkhead cross-section. So that's the main reason. But that's not entirely true, because if you look at Orbex, they have the idea for a coaxial tank where you have a smaller tank inside the larger tank, and they use that for thermal conditioning of the propellants. The idea that, there's a way to try to minimize the thermal transfer or whatever by doing it that way. But generally, long and thin means more surface area. So don't make it longer and thinner. That's why that tends to work. Also, putting two propellants side by side, you're not going to have the same mass of oxidizer and fuel, so you're going to have some mass instability if you do them side by side. Like if you look, the model's hidden behind the laptop, but if you look at the lunar module, the ascent module, it's asymmetric because on one side the oxidizer is different size than the fuel on the other side. That's why it looks a little off-center. Now it has a Q2 here. When rockets re-enter, all its kinetic energy is released as different forms of energy. So what percentage is released as light energy? What is thermal energy? What percentage in other forms? Okay, I don't have this off the top of my head, but what I do know is a re-entering spacecraft, most of the energy goes into the atmosphere around it, making the atmosphere hot. Some of that energy, invariable of course, ends up on the spacecraft. Now at normal orbital velocities, 7-8 kilometers per second, most of the heat is deposited in the spacecraft in terms of convection, that is hot gas just rubbing along the surface heats the surface. But as you go faster and faster, that becomes less important than the brightness of the plasma being so bright that it is emitting radiation. So there's a graph that shows as the velocity increases, you transition from this convective-driven region to this radiative-driven region for return from the moon. So I don't know how much, what the exact proportions are for how much goes into the atmosphere versus how much goes into the spacecraft, but yeah. What causes the twilight phenomenon? I presume the twilight phenomenon is why rockets look so amazing when launched during twilight. And the simple answer to that is when the rocket launches during twilight, it's in the dark, it's not illuminated by the sun. As it rises up high enough, it passes above the horizon from its point of view and is now illuminated by the sun. So we, in the darkness on the Earth, see this glorious gas cloud illuminated by the sun, and it looks so much brighter. That's really it. Okay, Phil Duckworth. Hi, Scott. Thanks again for taking time to answer these. If a sci-fi style space elevator, oh wait, we're onto space elevators again, cloned Emperor's optional, what would be the required orbital altitude for such a device? Would it be at risk from the dreaded space junk given it would occupy a fixed location with respect to orbiting debris? Okay, so beyond the fact that we probably don't reasonably have materials to do this, you have to have the midpoint be at geostationary orbit, and then you have to have a counterweight much further out. So it could be 80,000 kilometers, rough idea. The further you go out, the smaller of a counterweight you need, but the closer you get to the moon, and the moon of course will cause you to sway and stuff it'll cause all sorts of interesting oscillations. But that does mean inevitably that those lower few hundred kilometers, straight up, there's orbital debris in that area, satellites and things like that. And you're gonna have to come up with some way of dealing with that. Exclusion zone, tractor beams. Well, if you get tractor beams, why are you not using those to launch your spacecraft? Yes, space junk is obviously a no-no. And just regular meteorites or meteoroids are something that is going to slowly degrade your tower over time. You got to imagine there's sci-fi sci-fi worlds where explorers find the remains of an orbital tower from a civilization that died out 1 million years ago, and you've got this big tether sort of hanging out just slightly beyond geostationary orbit, and you can see a scar on the Earth on the planet where it has fallen down and left its mark. And then, of course, civilization there has all gone and done its own thing or something. Or maybe they have figured out how to travel faster than the speed of light and use their tractor beams and things like that, and they've just decided that this old planet is not that useful to them. So we only go there for sentimental reasons. It's the slums these days. Okay, so that's me up to like 20-minute mark. God, I still have questions going here. You can always add questions over at Patreon. I'm trying to post a lot more there because I feel that I really do need to supply some value to you wonderful supporters. And we'll see what other questions come next month. I'm Scott Manley. Fly safe.